So, good evening to you all. Welcome to today's session. Today's session, I'll be discussing with you regarding wildlife habitat suitability assessment and how remote sensing, GIS, or as such geoinformatics can be utilized for wildlife habitat suitability assessment. So, to start with, by habitat of an organism, we understand that it's a combination of resources and biotic and abiotic factors that promote the occupancy of individuals of a given
This
species
conference will now be recorded
and allows them to survive and reproduce. The main key is then the survival and reproduction. The concept of habitat preferences, and habitat association of species are very important in wildlife ecology and management. So the quality of habitat is related to the, as I mentioned earlier also, the quality of the habitat is related to the survival and reproduction of the species. So to study the habitat of an organism, it requires the understanding of its evolutionary history, ecological requirements, and interactions, the climatic history of the area in some cases, and even the history of movements of land masses for some of the species. Hence, detailed information on habitat requirement of major wildlife forms is very much essential for the habitat management as well as conservation activities. So identifying what exactly constitutes a habitat of a species or a population. This is the main focus on the when you see from wildlife management perspective. So as you know, there are many threats to wildlife. This is mainly due to increase in anthropogenic pressure. Then natural environments also have been severely disturbed. All due to this, mainly due to this anthropogenic pressure, the environments, the natural environments have been severely disturbed. Or it is not over one country, it is all over the world. So this anthropogenic disturbances on natural resources have the prime causes of decline in wildlife. So an encroachment of natural habitats for various purposes like agriculture, grazing, poaching are the major threats to wildlife. Now, coming to habitat evaluation, why you want to do habitat evaluation at all? So the design of studies that identify habitat condition requires considerable understanding of the needs and perpetual ability of the species. The spatial and temporal scales at which the study is to be conducted, and methods of measuring the environmental features. As mapping and monitoring of wildlife habitat has become an important component which is used to interpret the species distribution, to evaluate the dynamics of population, and to predict the abundance of the organism. Hence, in this context, the habitat evaluation is crucial, the most important step for planning wildlife conservation and management activities. So habitat evaluation for its suitability or unsuitability of any species. It requires a lot of information about its biotic as well as abiotic environment. Now comes the role of geospatial technology. Remote sensing has been identified as the most effective technology for mapping and monitoring of wildlife habitat. And geospatial technology, that means which includes remote sensing, GIS, and GPS, along with the habitat suitability index model. This can provide a quick, efficient, and cost-effective method for evaluation of habitat of any species. It has become Geoinformatics has become a vital tool for habitat mapping because of its broad, mainly for as remote sensing can cover large extent. which cannot be large extent both spatial as well as temporal, which cannot be done with field-based approaches. But here I must mention that it is not like I forget the field data and then I only through remote sensing I'll be doing this study. This is not the case. Here is an integration of field data and remote sensing data. So integration of field data with your remote sensing, and based on some habitat suitability modeling using GIS-based model, you characterize or the habitat suitability or assess the habitat suitability of any species. If you do field-based approaches, they generate measurements with high accuracy, but no, when you are studying for a larger area, there is a time constant is there. So as I said, like you cannot take only this remote sensing and do. You have to integrate the field surveys, field data, as well as with the remote sensing based remote sensing data and formats to get an idea of the species or the suitability of a species in a particular habitat. Now, geospatial technology is has been used as a tool for wildlife studies, ranging from evaluation, suitability analysis, and further even for wildlife border monitoring as well. So habitat evaluation is for predicting the suitability of a species. That means you will at the end you will generate let's say map where the it will show the areas which are suitable for the habitat for the species, which are unsuitable or less or least suitable for the species. So habitat suitability modeling is one such technique which provides the probability that the habitat is suitable for the species and also give the probability of the species that can occur in similar habitat. So if you see the habitat suitability history of this habitat suitability modeling, since very early in 1970s, expert opinion has served as a primary information for habitat evaluation. So the person with high experience in this area or who have worked, let's say, for a species for let's say 20-30 years, they gave like based on their opinion or based on the experts opinion, we used to give and they used to give weights for the various layers, and then ultimately they used to make a map. So in the simplest form, habitat suitability, it could be an equation of additive, multiplicative, or logical form with the coefficients, of course, and then this represents the relative value of environmental features. And then the coefficients are generally scaled between 0 and 1. 0 means least suitable or you can say unsuitable, and the 1 is highly suitable. But through the time, the modeling process has evolved. Like as I mentioned, like earlier people used to do with expert opinion. Let's say I have some layers, and then how I'll integrate these layers based on the expert opinion. I'll give weightage to the particular layers, and then using additive or multiplicative method equation, I can add up these layers and get a equation. I get the habitat suitability map. So this is totally based on the weightage or totally based on expert opinion. So in the habitat suitability model, when you give if the index or the final output has higher value, that means if the value of the index is high on a particular location, the chance of species occurrence is greater. Now, to continue with that, there are many actually habitat suitability models that have been used, starting from a very simple model to the advanced models as well. So started with habitat ranking, like whether based on my or the expert opinion, this habitat is suitable for the species, or let's say this forest area or this density classes are suitable for the species. Like that, the habitat rankings were done earlier. There are many various approaches for habitat suitability models, like envelope models. Then you have maximum entropy model or maxTime. Then rule-based models like GER. Then multi-criteria analysis like analytical hierarchy process, splines, classification, prediction trees, geostatistics, and machine learning based models, as well as ensemble models. So I'll give examples of few of these models and how these were used for assessing the habitat suitability of a particular species. Now, to start with, this is special multi-criteria modeling have been used for identifying the areas which are potential habitat for a particular animal. Now, to start with, here this multi-criteria, this is used for analyzing the choice of best decision in a complex planning. So this is primarily concerned with how we combine information from several criteria to sorry, to form a single index of evaluation. And in this case, analytical hierarchy process is widely used. One of the technique for which comes under the multi-criteria modeling. This AHP was developed by SETI. Now, in AHP, now basically, what is the role of AHP? So, suppose we have, let's say, some maps. Let's say map 1, map 2, map 3, map 4. This depends on the species. I'll show you an example how these maps were selected or how these layers were selected. Once your layers are selected, then this should be standardized so that it comes to the same platform. Means, like, suppose the map 1 is vegetation type or land use map. So these are this has categorical variable. Let's say map 2 is elevation. So this is continuous variable. So these kind of things should be bring this should be bring to a same platform so that all these can be combined together. So this needs to be standardized first, and then you have to combine all these. Now, how will combine? While combining, that means you are giving equal importance to all, which is not the case. So again, it is species specific. So giving the weights earlier, as I said, in 1970s or in the earlier times, people used to give these weights based on the expert opinion, but you can give weights also using. So after this, people have started giving these weights using AHP or analytical hierarchy process. So this analytical hierarchy process modeling, you can decide, you can calculate the weights to be assigned to each of these layers, so that when you combine, you get an output which is a habitat suitability index map. Now here I'll show you an example. What I did in area. This is near Hardwar in Uttarakhand state of India. Now, the study was basically on swamp deer potential habitat using multi-criteria. So here AHP was used, analytical hierarchy process used. Now, you can see this is in this case, least square image was used because the area was not that big. So here least square imagery was used, and then a study area was extracted. In the study area, this was done in a conservation reserve called Jil Conservation Reserve. So with the Jil Conservation Reserve, the center, we have taken a 15 kilometer by 15 kilometer area, so that I'll show in the next image. Yeah. So this is the here. This is the area, study area. Here is a conservation reserve called Jil Conservation Reserve. So what we have done, keeping this in center, we have taken 15 kilometer by 15 kilometer area over this, so that our aim is to whether can we find similar areas in nearby this thing also. So this is the habitat, is a known habitat of swamp deer, but can we get similar habitat, or can we propose using remote sensing GIS or this kind of multi-criteria analysis, can we identify similar habitat in nearby areas? So first of all, the vegetation land use map was prepared, and then from Google Earth and also using topography, the drainage, road, and settlement layers were generated. Now here you can see this is basically distance from drainage, distance from road, and distance from settlement. So as you see, when there is uh, in this case, let's say swamp deer, so potential habitat would be away from this road and settlement and near to the drainage. So since the area elevation was not considered at all in this area, so these are the four variables which are considered: position and land cover time, then drainage, road and settlement, and these were then standardized, as I showed in the earlier slide here. These were standardized into a same this thing, index. So based on the suitability of this animal, these layers were standardized into vegetation index map, drainage index map, road index, and settlement index, and ultimately they were combined using analytical hierarchy process. Through these, weights were calculated, and after this modeling, modeling, the habitat suitability map was generated. Now, if you see this line here, so this is the area here. This is the photograph of this area. This is the conservation reserve. You can see this swamp. This is the area. Now, the output map which I showed here, the right hand side. So this is the area. Now, here you can see this. Of course, this was known area, which is potential habitat for swamp deer, as swamp deer was there. So we could identify that nearby area is also suitable. Now, this dark green color, this says this is suitable area. So through this multi-criteria modeling, we could able to identify this area as well as the highly suitable area. And this, this is the moderate suitable area. These are the moderately suitable area, these areas, and these are least suitable areas. So we can categorize this area using this the multi-criteria analysis or multi-criteria based modeling. We could identify the categorize the area into highly suitable, suitable, moderately suitable, and least suitable classes. Now, sorry, coming to this. Now, here you can see this is Jilmil Conservation Reserve, which is this. Now, even in our field work during the field visit, we have observed that the animals which stay here in this area, they they move through these padlands, agricultural lands, to the river here. So their path is like this. They come and so basically this is also wetland kind of. This is also they practice agriculture, but it is this is not the agriculture which is practiced here. So this like this, we even give a suggestion also. If there is a small village here, so if this can be relocated to some other places, so everything could be considered under the conservation reserve if possible. So here you can make a suggestion also. What we have found is, out of this total area, the habitat suitability status, highly habitat suitable status is around 4.6 kilometers square. But if we consider the habitat suitability status inside the conservation reserve and outside the conservation reserve, inside the conservation reserve, of course, the suitability will be more. But if you see the outside the area, this is very interesting. When we see highly suitable classes, around 2.6 kilometers square area, which is suitable, but it is not under conservation reserve. So using this kind of modeling, you can also propose like whether as this area is also under suitable, highly suitable under the swamp deer, this can be extended so that they get a bigger area, bigger habitat rather, which is found to be a highly potential area. So based on these studies, suggestions can be made for proper wildlife management as well as conservation. As you can see in this case, highly suitable area is around 2.6 kilometers square, which are not considered at all under the conservation reserve. And this is the total scenario of this area, which is 15 kilometers by 15 kilometers. Similarly, so this is what I showed as multi-criteria analysis. But for logistic regression based model, or you have other models, neural network based model, or let's say Ensemble models, you need to have the presence location of the species also. So in this case, we divide the variables into mainly two categories. One is a dependent variable. Dependent variable is basically presence location of the species. This could be direct sighting or indirect evidences of wildlife. So GPS is used to note down the geographic coordinates of either presence location, direct sighting, or the indirect evidences of wildlife. And then the point location map is generally overlaid on the satellite image to identify these points where the animal were sighted or indirect evidence was found. So far as independent variables are concerned, the independent variables may it will vary from species to species, but generally, I've given a table where these parameters are generally used, like vegetation type, land use. The source you can get from remote sensing data, vegetation canopy density from again remote sensing data, then elevation we have remote sensing data like SRTM, then Aster CartoTM, as well as LOS TM also is there. Slope can be derived from this DM. Aspect also can be derived from DM. And then road network you can get from high resolution data or from other sources as well. Settlement also can be derived from high resolution data, topographic maps, Google Earth, or from other sources, open sources also. Water body also can be derived from this. So these like in some studies you can use this landscape matrices. So this can be computed using some of the tools like page analysis tools, landscape fragmentation tool, FlexStats. If your speed now, main concern here is the species requirement. And first of all, the species in question or the target species should be studied properly. Its habitat should be studied properly, and then you try to see whether these parameters can be addressed through remote sensing or not. And if it can be done, then how and what could be the source of this? So in case of, let's say, carnivores, you should have prey density data also. So in the modeling for carnivores is slightly different. So you model basically the habitat suitability of prey, and then these prey suitability maps will be an input variable for the carnivores. In some of the studies, you can use climate data also. Climate data you can get from Berkeley or CHELSA data sets also. So these are the various climate variables. They have bio 1 to up to 19. So these are basically temperature, the varies from annual mean temperature to maximum temperature, mean temperature. So basically, its precipitation is and temperature, all the variables can be used. So this is available in, let's say, Berkeley data as well as in CHELSA data. So I'll show you an example where this point or the presence points are being used. In the earlier study in multi-criteria analysis where HP modeling was used, here there you don't need actually this point data, but for verifying the verifying your output, you can, if you have a point data set, you can verify using those. So regarding this habitat suitability of let's say musk deer, here we have done a study on we have studied we have mapped the suitability of habitat suitability of Himalayan musk deer. So this is the smallest Himalayan ungulate is anyway being in the cold environment. So when you study, as I mentioned earlier also, when you study when you do this habitat suitability modeling of the species, you should know everything about the species, habit, and habitat of the species of the target species. So this this occurs in Bhutan, northern India, Nepal, China, and this is considered as in Appendix 1 of the CITES and is endangered, declared endangered by IUCN. Then it is also included in the schedule on the wildlife schedule on species. And this is this animal is generally found in the high altitudes, generally from more than 2,200 to 4,300 miles. So this musk deer population is declined drastically, mainly for its poaching because of its musk. So I got a very early, old reference where it says per kg of musk is around US $55,000 per in international market. Now this is very old reference. I don't know the present value of this, but anyway, these are killed because of this mask. Now, hunting is responsible for the mask deer. In addition to that, habitat destruction is also is one of the reasons for this habitat shrinkage and which affects the habitat of the species. So, for this study, what we have done, this is done in here. Kedarnath Wildlife Sanctuary. This is again, in Uttarakhand. Here, in this case, also we have taken list 4 data, and using list 4 data, and in this case we have taken Carto NEM digital elevation model, and in this, from list 4 data, we have interpreted the vegetation type or land use map. Now, this is one of the variable, and then the dependent variable is mass deer presence point. So where the animal was sighted or the indirect evidences were found. And then using the other variables which are considered were elevation, slope, aspect. And these were derived from DM or the digital elevation model. And then patch cohesion index, one of the parameters of landscape matrix, was also considered in this case, and this was generated from the vegetation type land use map. So in this case, if you see, this is the dependent variable, which is mass deer presence points, and the independent variables are vegetation type land use map, elevation, slope, aspect, and patch cohesion index. And using a binomial multiple logistic regression model, we have mapped the potential habitat of the species and ultimately validated with the ground point from this presence points, because around 70% of the points were generally used for modeling, and the rest 30% presence points are generally used for the validation purpose. Now, if you see, these are the glimpses of the field. Now, here this is Kedarnath Wildlife Sanctuary. Now, these are the areas which are very suitable for this animal. Now, this animal is very shy, and they prefer these areas, where they don't come out like in open areas like this. They will be near this area. In case of any disturbance, that it will go inside this this small bushes like this. So here you can see. So this is a perfect habitat. So they will come here. They will graze here, and if they get any sound, also they will just go to their secret places like this. So we could sight here in this part. We could sight the animal after 3 days of waiting. We could sight the animal mass deer here, but when a small, in case of a small sound, if they hear, they immediately moves very fast in this area, so that you cannot trace. So these are the perfect habitats, where there is a grass as well as forest like these tree line areas. These are the perfect habitat for the animal. Now, the dependent variables are the presence points. So these are the areas where we could sight the animal or got the indirect evidence of this animal. So these are the field points. Now, these are the field points, and based on this dependent variable, you combine these with the independent variables using this partial modeling, which in this case is a binomial logistic regression model. So this is the elevation map. This is the slope. This is vegetation type land use map. This is the aspect map, and this is patch cohesion index. So combining this with respect to these points, we could generate the habitat suitability model, a map. Now here you can see this dark color is highly suitable. Then you have suitable, then moderately suitable, and least suitable. Now, these maps are very good from point of view of wildlife management, as well as from, like, say, some development activities. So this is of course a protected area, but if you do it in a, let's say, the area which is not protected, you can also suggest, like, suppose some development activities is proposed in these kind of areas. You can say this should not be allowed in these areas, as these areas are highly suitable for the animal, or the, in this case, there's a mass deer. So this can be suggested. So development activity should not be carried out here. Maybe in these areas it can be carried out, but for the for as a species is very important. This is scheduled one species, endangered species. So development activity should not be allowed in these areas. It can be allowed, but of course, here it should not be allowed. So the maps, when there is this kind of maps are not there, is very difficult to identify the areas which are now highly suitable for the species, since we have only the points. So when the maps are there, these are very good, important input for the wildlife habitat management as well as conservation point of view. And simultaneously, you can take out the you can calculate the area under each class. The whole area, how much area is highly suitable, moderately suitable, or suitable for the species. Similarly, we have intersected this with the vegetation type map, and we could see this subalpine forest has the maximum area which are highly suitable for the species. So, so this is the area. This is of course, this alpine pasture is not that suitable. Most of the area or the highly suitable areas mainly confined to subalpine forest. So, as I showed in that here also, the species prefer this area rather than this area or this. So they prefer this kind of areas. So we could validate this model also, and high accuracy also was observed in this case. So this is how, like, when we can get conclusion also. Suppose in moist temperate forest, you get highly suitable area is 0. So they don't, they are not found in the moist temperate forest. They are found in the subal. So this kind of analysis will show you, like, where which forest type they are generally found, and you can verify also from the your field knowledge. So moving with that, I'll show you one more example. So in this case, a bird. This is called rufous necked hornbill, and IUCN status of this animal is of this bird is vulnerable, and these they are generally found in eastern Himalaya, northeast India, which includes northern West Bengal, some Arunachal, Meghalaya, Manipur, Mizoram. These are categorized as Schedule 1 species of the Wildlife Protection Act, and also considered as flagship species of the tropical forest conservation. Now, habitat generally they're frugivore and they're frugivore and inhabiting mainly in the subtropical, primarily evergreen and deciduous forest, and threats that dependent on large trees for feeding and nesting make it susceptible to deforestation, habitat degradation through logging, and Northeast India this shifting cultivation clearance for agriculture. So we have done a study on the habitat suitability modeling of this bird. It's called a rufous necked hornbill. In this case, now this is the distribution map of rufous necked hornbill. You can see here. So most of the part of Northeast India, then Sikkim, Bhutan, and northern Bengal also. Then if you see Indian context, it's here only. So we have taken this whole Northeast India and the northern part of Bengal as the study area. So like this, Sikkim, northern Bengal. So northeast, all the 8 states and northern part of Bengal. So this is the study area. This study area study is yet to be published, yet to get published. So very recently done study, and here we have taken the species occurrence data. This I'll again come to that from where we got the data. So environmental variables in this case we have considered bioclimatic variables. As I mentioned, all these bio 1 to bio 19 variables. Then elevation, land use and cover, normalized difference vegetation index, distance from the water body, distance from road, distance from settlement. These were the environmental variables that were included in the study. And then we have done the test for correlativity, so that we can see, like, if there is a correlation, high correlation between 2 variables, we have taken one. We have or highly correlated variables we have removed. I will show you the result of this also. And then the selected variables were used using a model called biomod 2. It's an Ensemble model. And then what we have done is we have identified the importance of environmental variables in creating the potential distribution of the species and the present potential habitat distribution of macro species. And one more thing we have done is using the future climatic data in 2014, 2017, using only climatic data, we we could predict the future potential habitat distribution map of the species. Now, to start with the data, like this part, the species occurrence data. So basically, in this study, we have concentrated mainly in the freely or open source data, freely available or open source data in this case. So we relied on mainly the Global Biodiversity Information Facility, then IIRS, then of course through literature wherever they have, because we need presence points or the latitude longitude of the species that are found in these places. Some of the literatures were also the presence point locations which are mentioned in some of the literature also considered the study. And you can see here you have accessed this site in 19th June. So this is we should mention this also, like when it was accessed, because after that there may be addition also in that data. So this is also accessed in the June 2021. This is also accessed in 2021. So main source for getting the species occurrence data were the GBIA, for the Global Biodiversity Information System. So basically, this is latitude longitude information of the presence points of those species, eBird also, and literature. So this is the dependent variables. So for independent variables, which are the environmental factors. So basically, I'm talking of this part. So this is what I mentioned, the source of the data. Now I'll come to this part, which is the environmental variables, which includes bioclimatic variables, elevation, land use and cover, and DVI, distance from water body, road, and settlement. Now, for doing that, in elevation, we have taken the SRTM here. Then you can see we have used the Google Earth Engine also to extract this. So these are the sources of the data sets from where we have selected the data. Land use and cover, we have taken the Moody's land use and cover product. And then NDVI was taken from Moody's data. And then water body current distance, again, these are the sources or the data products that have been used. These are the variables or the factors that are used, or you can say environmental factors. And then these are the data sets which corresponds to these factors, and then the data sources. So in these bioclimatic variables, we have used CHELSA climate data. Now this is the link of the website of CHELSA. Now, if you see these bioclimatic variables of CHELSA, this is again bio 1 to bio 19. All these variables are being used, and these are different aspects of temperature as well as precipitation. Now, using all these variables, all these variables. So basically, this is the independent variables and dependent variables. Now, I'll come to this part. Now, when I'm using so many variables, so basically in bioclimatic variables, there are 19 variables, then there is 1, 20, 21, 20, 24, 25, 26. So there are 26 environmental variables, but there may be correlation among the variables also. So to reduce, select the uncorrelated variables, we have done this Pearson collinearity test, multi-collinearity test was conducted to examine the correlation among all the variables, based on which the highly correlated variables were excluded from the modeling process. So the variables which are uncorrelated, those were selected finally for modeling. Now, so in this case, wherever I'm getting, let's say this kind of thing, let's say bio 11 and bio 8. So these are highly correlated. So I have so likewise there will be other like bio 8 and bio 10. This is also highly correlated. So instead of taking 3 variables, I've taken 1 variable, like that. So which the relationship or the correlation between 2 variables, if this is or the variables is more than 0.8, these were excluded, and only the uncorrelated variables which are less than 0.8 correlation, they were selected. So in this case, out of this all these 26 variables, these many variables were selected, which are uncounted. You know, so you can see from 19 variables, we could get only 7 variables. So others were highly correlated. So these variables were then used as an input to this biomod2 ensemble modeling. Biomod2, this is done in R package, R environment. So biomod2 ensemble model was used in this case, and these layers were the input variables in this case. Now, what the biomod does is when you use biomod, there are these models are generally these models are used in that biomod2. Generalized linear model, then generalized additive model, then surface range envelope, then artificial neural network, generalized model, and classification and tree analysis, flexible discriminant analysis, random forest, and multivariate adaptive regression spline. So these are included in that ensemble or biomod 2, and here 80% of the data were used for calibration at these points, and 20% were used for the validation of the models. Now when you see the variable importance, in this case, out of this also we have calculated the variable importance, which variable is most important. Out of the selected variables, we found that bio 13 is basically the precipitation amount in the wettest month has the highest significance on all models, followed by 15, 19, 3, and 12. So these are the most important variables. So out of the selected variables also, as I showed here, out of these selected variables, we could learn that this is the most important variable when it was found to be the most important variables in all these models. Highest influence in all the models, followed by 15, 19, 3, and 12. So here, using those variables, we could map. So this is the final output, which says the current distribution of, let's say, the species, which is rufous necked hornbill. Now we can see these areas here, northern part of, let's say, Bengal, and this part here. Then here you can see this part, like this area, number variant on here, this area. So these, wherever you see green color thing, these are found to be highly suitable for this animal, for this the bird, the rufous necked hornbill. Okay. Now again, these are the areas which are, let's say, moderate. So you can see a scale from low to high. Low is this reddish thing, this is low, and yellow thing is, let's say, moderate kind of thing, and the greenish thing is the highly suitable. Now you can see based on these dependent variable or combination of dependent variable and independent variable, we could get this, and this the major highlight in this study is all these data sets were taken from freely or open source data, even the software event. So the data sets, the presence points were taken from GBIF, eBoard, and some literature. Then all these products, all these satellite data and products, these are also freely available. The environmental variables and such, and the platform, let's say you have used Google Earth Engine or the R software have been used, these are also freely available. So it's a study which is which is used freely available data or product, freely available algorithm, freely available platform to complete or get the output of this study. Now, as I said, one more component was there, which is this is the current projection. Let's say this is the current projection of the same thing is here. This is the current projection, but our objective, one more if I go back slightly in methodology, there is one more thing, like using future climate data, can you predict the future potential habitat distribution of Nepal species? So if I come to this, so this is the current distribution. So here it is showing the current distribution, and in 2040, in different SSP scenarios, what is the future projected distribution of the species based on the climate data. So this is the, let's say 2040, and then this is 2070. Now again, these are based on 2070 climate data. You have current potential distribution, and then you have the future distribution as well in different pathways, like SSP1, SSP3, and SSP5, and this is 2070 scenario. So is like you are studying the current projection area or a current distribution of the species, and as well as you can take the future possible like future projected distribution of the species based on the climate data which are available for 2040, even 2070 as well. So current projection distribution, current distribution, and future projected distribution of the species are also mapped. Now, to conclude, I must say that knowledge about this ecological and geographical distribution of the species, it forms the basis for understanding the ecological and evolutionary determinants of spatial patterns of the biodiversity. And conservation of species can be achieved through in-depth knowledge about the geographic distribution and pattern at different scales. And these quantitative evident models and predictive distribution maps are now are very important tools for conservation and management of wildlife habitats. And the species distribution models using using this species and ecological relationship are one of the most important tools for predictive modeling as well as mapping of suitable habitat of the species. Moreover, its current distribution as well as the future projected distribution also can be mapped, which is a key for conservation and management of any wildlife species. So geospatial technology has proven its potential in wildlife habitat analysis over the past few decades, and will continue to do so in the future as well, with the advent of new remote sensing data in combination with new techniques. So here the see, one is dependent variable, another is independent variable. So we combine this through a modeling approach to get the output for the species distribution model. So there are new data sets also coming up, so which will give new variables also, as I mentioned in my last lecture also in LiDAR. So suppose in this case also, as the species was like say fluvivirus and all, one could have been one additional variable could have been included is the height of the or the forest canopy height. If we could have included the forest canopy height, it could have given the better representation of habitat what it has given. So in future also, this can be included also as this also can be included to get a better representation of habitat. So it's not only the active remote sensing data, also it's not only the passive remote sensing data, the introduction of or the availability of passive active remote sensing data, and with a combination of several techniques. So it is technique like as I mentioned, the earlier thing was like giving only a ranking based on expert opinion, then multi-criteria analysis, then using some logistic regression model. Now people are using like Ensemble models also, or models for predicting species. So there is a huge improvement in the availability of data as well as a new technique, and this will in a future also there will be many data sets will be coming up, and there will be new techniques also has to be devised for integrating this field information or field data with the remote sensing data using this geoinformatics or the geospatial technology to get better representation of the habitat or better assessment of the potential habitat of wildlife. So that's all for this today's session.